IMFs because talking about IMFs, right? Well, first of all, I guess, what are the three IMFs that we were talking about yesterday? So give me one. Start with the weakest.
Oh, you said give me one.
Yeah, give me the weakest one.
It's not default.
Nope. What's the weakest intermolecular force?
IMF. Oh my God.
McKenna. London dispersion forces. Okay, that's the weakest. Then Dean, what's the next? Dipole. Stronger, yeah. Okay, and the most strong, though? Hydrogen bonding. Yep. Okay, so those are the three, right? So those are, we're talking about forces between molecules, attractive forces between molecules. We could also describe those as, you've probably heard them described as cohesive forces, right? Cohesive or cohesion, right? That is molecules attracted to the same molecule. Okay, so what I mean by that is we're talking about water molecules being attracted to other water molecules, right? And you've heard these in biology freshman year. Some of these words, cohesion. Okay, what's the other one that's similar to this? No, it starts with an A. What's that? Adhesion, yeah, adhesion. Right, adhesion. You guys know what that is? Yeah, molecules are attracted or sticks, right? To different molecules. All right, that's the key component there. Okay, whether it's the same or different molecules, you have cohesion or you have adhesion. Okay, so and that's really important. So that's just another set of vocabulary words that, like, we might use to talk about IMFs. Right? We could talk about, oh well, there's some cohesion here, and the cohesion is being caused by the intermolecular forces that are there. Maybe the dipole moments that that the molecule has, or whatever. Right? Okay, so those are just some other words that we might use and we're going to use that we will probably use to describe some of the things that we're seeing here. Okay. All right. So properties like surface tension, right? Surface tension. Surface tension. What causes surface tension? Molecules being attracted to each other, right? The more they're attracted to each other, the stronger the surface tension, right? So we have a paper clip, right? You guys have all done this before, probably, maybe not. All right, if you got a paper clip and you go and set it on the water, yes, right? You can see the surface tension there, can't you? Can't you see that? Look at that. It like curves down and like it doesn't break the surface. That's so neat, right? Okay, so like that's the water molecules like hold my hand, like holding hands, okay, like linked together, okay. That's surface tension. How strong they can hold on to each other, right, before they break. All right, so that's awesome, isn't that so cool? Like, so those little insects that water, what do we call it? The water striders, yes. The water bugs, the water striders, they're shooting along the surface of the water because of surface tension. Okay, very cool, right? I mean, I love the fact you can even see it like bending and around the paper clip there. That's so cool.
Look at it, or is that just only when
No, you can actually see it when it's like just looking at it right now. You can see it. But the fact that we can zoom in on it.
It's kind of hard to see because the screen is lighter than what it actually looks like. That is cool.
Yeah, that's cool. Right? Okay, so surface tension is all related to IMFs. The stronger the IMFs, the more surface tension there is. Right? What kind is that cohesion or adhesion? Cohesion. because it's water molecule to water molecule, right? Okay, so that's great. All right, so capillary action. Maybe. There we go. So capillary action is just talking about water or a liquid. We're talking about liquid moving up a small glass tube. Okay, just water going up a small glass tube. Okay, that is capillary action. Now, you'll notice water and mercury are different, right? Is water polar or nonpolar? It's polar, okay? And what about mercury, just Hg? It's nonpolar, yeah, it's nonpolar, okay? All right, so it's unique. So what happens, though, is it's very interesting, okay? Water forms a meniscus, right? Like it's climbing up the sides of the glass, right? It's climbing up the sides of the glass. You can see the meniscus there. So how is water climbing up the sides of the glass? Why is it doing that? Why is water moving up the sides of the glass? Yeah, Claire. Yeah, water is attracted to the glass. So what does that mean about glass? Is it polar or not polar? Gotta be polar. Glass is polar. The surface of glass is very polar. Okay, so water forms a meniscus because the H2O is attracted to the polar surface of the glass. Of the glass, right? They're both polar. Polar attract polar, right? They can be attracted to one another, like a dipole-dipole moment. That's what's going on here. And really, even more specifically, the surface of glass has a bunch of H's bonded to O's that are then bonded to, like it would be like this is the surface of SI. It's like there's silica molecules bonded all in there. Like if this is the outside, so what can these guys do? Yeah, they can hydrogen bond with the water. The surface of glass can actually do hydrogen bonding, right? So that's talk about attraction between water molecules to the surface of the glass. Wow, right? Water molecules can do hydrogen bonding too. So that's why they climb up the glass, because they're so attracted to it. There's a lot of adhesion, right? That's an example of adhesion, right? Water being attracted to a different substance like glass. That's adhesion. Okay. If you're a polar substance, you'll form a meniscus. It's just a matter of the more polar a substance, the deeper the meniscus, right? The less polar, the less deep. Absolutely. Yeah. Okay. Where mercury does the opposite, right? It forms that reverse meniscus. Look at that. It's upside down. Right? Because mercury is, the Hg is non-polar. So it's held by the glass. Right? Mercury is more attracted to itself. Okay? So this is kind of the key line here. Okay, mercury is more attracted to other mercury molecules than it is the glass. Okay? That's really neat. Okay, it's really pretty interesting. Right? So if you're polar, you can be attracted to other polar substances. All right. Viscosity. Right, so all this is resistance to flow. Like, can you guys think of a substance that has pretty high resistance to flow? Yeah. Yeah, syrup is a good example. Yeah, like syrup's a good example. That is high viscosity. Okay, high viscosity. The more sugar it has, the more viscosity it has. Okay, sugar molecules are polar. They can actually do hydrogen bonding. Okay, so that's always interesting. But so increasing IMFs usually equal high viscosity. But one other thing, there's a caveat to that. It really goes hand in hand, but large molecules, okay, that have long chains, so like oil molecules, yeah, they get physically entangled in one another. Like at the molecular level, they're like tangled up in one another. So that's what causes them to hardly flow at all, right? Have any of you guys ever seen the pitch drop, right? Where they're waiting on the pitch to drop, okay? It's the most viscous substance known to man, right? I couldn't even tell you, I don't remember. They have like you'll have to look it up, okay? So, I don't know.
Have they been like pouring it for like 10 years?
It's some ridiculous amount of time, is what it is. It's like going through a funnel and the drop like forms really slowly and then finally comes down. Hello. Analytical balance? Sure. Hang on 1 second. So that's viscosity, basically just resistance of flow. Okay. Vapor pressure. We're going to do a demo with this for our lab. One of the first people we'll do there. But vapor pressure, substances that have low intermolecular forces have high vapor pressure. They evaporate real easily. Because think about what a molecule that's in the liquid form needs to do to evaporate. What does it have to break free? Not necessarily bonds, but no. What are we talking about? What keeps one molecule traded to another one? Yeah, the IMFs, right? It's got to break free of those forces, those attractions, in order to evaporate. If there's not much attraction between one molecule to the other, it'll leave pretty easily. Okay? But if there's hydrogen bonding and dipole-dipole interaction, it's going to be very difficult for that molecule to escape the attraction unless it's got enough energy to leave, right? Okay, so that's why water takes so long to boil, right, and things like that. So very high intermolecular forces. All right. Okay, so the same thing goes along with volatility here, right? Low IMFs mean that you're very volatile, right? Okay, and then with solubility, all right, they go hand in hand, right? You guys have all heard the term like dissolves like, right? Right, so if you're polar, you can dissolve other polar substances, all right? So polar can dissolve another polar substance? Yes, that's true, okay? Do oil and water mix? No, right? Like that, polar and non-polar things don't mix. We can shake them up, mix them up as much as we want. They'll still separate, right? I have this bottle, I call it the frustration bottle. Okay, it's got oil and water in it. You can shake it up as much as you want. You're going to end up frustrated at the end, okay? Because they're going to divide apart and you'll have oil on top, water on the bottom again, okay? What about ionic and polar? Yeah, they can, right? Because what's the biggest, there's a huge, massive, literally huge, massive example of ionic substance and a polar substance interacting. Can you guys think about it? Salt water, yeah. The ocean, prime example of ionic and polar, right? You have a bunch of salt in there, which is an ionic compound, sodium and chlorine dissolved in there, and water being the polar substance. There you go. Okay, ionic and nonpolar. Right? Because in order for an ionic substance, an ion, it can interact with, the other opposite end of a polar compound, right? If you're a positive sodium ion floating around, you can interact with the negative end of water molecule. Okay, there's some attraction there. Right? Okay, so let's sum these up here. IMFs increase, so it's intermolecular forces increase as you have more and more London dispersion forces or dipole-dipole interaction or hydrogen bonding. What happens to the melting point of a substance? It increases. What about boiling point? It increases. Vapor pressure? Decreases, yeah. So less will go into a vapor. Volatility? Increases. Viscosity? Increases, yeah. Okay. There we go. All right, so on the flip side here, okay, notice up here, this is same thing as 1 atmosphere, right? 101.3 kPa, same thing as 1 atmosphere. And you can see there's the temperature there. Notice when, something to keep in mind here is when vapor pressure equals atmospheric pressure, substance will boil. That's something to understand there, okay? So when vapor pressure equals atmospheric pressure, the substance is boiling. Okay, so notice where water crosses 1 atmosphere on our graph. It's the temperature. 100 degrees Celsius. Okay, so we're just looking here. 100 degrees Celsius, water would boil at 100 at 1 atmosphere. Okay, so if you're less than 1 atmosphere, right, the amount of the temperature needed is less and less. Okay, because you don't need as much energy to get those molecules to evaporate and ultimately boil. All right, so that's why, like cooking a cake or something, is, you know, the higher you go up in altitude, you need to use different instructions. You might have to cook the cake longer or at a higher temperature because water that's in there is not cooperating. Right, it's going to boil at a lower temperature and things like that. Okay, like you go to the top of Mount Everest, right? Water's going to boil up there around like 90 or 88 degrees Celsius. Okay. So, normal boiling point for on this graph for chloroform and ethanoic acid. The normal boiling point, which is usually at sea level or 1 atmosphere. Got to read the graph. Yes. Yeah. 60 degrees and about 121. Okay. At 60 kilopascals, water would boil at what temperature? It's 86. If atmospheric pressure was 80 kPa, which substance would boil at 60 degrees Celsius? So that's this point on the graph right here. Which substance is going to boil by that time? It's which one has the highest intermolecular forces? Bianca? D. Yep, at the highest boiling point. One of them has the lowest heat of vaporization, least amount of heat needed to boil it, vaporize it. All right. Okay. All right, so let's do our demo.